Sup guys? Sup guys? So now we have a rather weird looking problem. If we're supposed to prove that if x plus 1 over x is rational, that implies then that x to the power of n plus 1 over x to the power of n is also rational. Okay, so just starting out, what we'll do is that we will think about this factorization rule. Okay, so if we have x plus 1 over x squared, what is that? That is x squared plus 2 times this, so that's just 2, and then plus 1 over x squared. Okay, so you might see where I'm going with this, okay? You might. So, how will we do this? We will do this with a proof by induction. 1 second. So, quick recap. What is an induction? Proof by induction. Okay, so first, we'll just prove this for a simple case. Okay, so let n be equal to 1. Well, yeah, that's obvious. If 1 over x, then just, well, yeah, okay, x plus 1 over x. That is just equal to x plus 1 over x for all x. So it's, if one of them is rational, then obviously the other one is rational. Okay, so yeah, that was step 1 in the proof by induction. Step 2 is that we assume it works for some given n. So assume the statement above. Okay, so I'll call this star. Assume star and then prove star when we let n be equal to n plus 1. Okay, so this is more, you think about this as like programming, not real math, because then this is ridiculous. So basically what we have to do, okay, so we assume that this property holds, and then we're supposed to prove that, well, we just exchange n for a n plus 1 here. So we're supposed to prove that x to the power of n plus 1 plus 1 over x to the power of n plus 1 is rational if x plus 1 over x is rational. So what do we do with this? Well, I suggest that you think about the factorization that I did before. So, okay, if we just were to multiply these two, what would we get? Well, we would obviously get something like this, not exactly, but we'll just try. Okay, so we say that this is equal to x plus 1 over x times x to the power of n plus 1 over x to the power of n, and then we just look what we have to subtract. Okay, so what would this give us? This would give us x to the power of n plus 1, and these two multiplied would give us that. But okay, what else do we get? Okay, so we have to take minus 1 over x to the power of n minus 1, and then, okay, so that's that one and this one then. Okay, and then we also have to subtract by x to the power of n minus 1.
And this is just equal to x to the power of x plus 1 over x, times x to the power of n plus 1 over x to the power of n minus x to the power of n plus 1 plus 1 over, n minus 1 over over x to the power of n minus 1.
Yeah, okay. So here it gets a bit tricky. So, okay, essentially this problem, I would say, is very easy intuitively, but it might be a bit difficult to write down. And since you know I'm not writing down everything very explicitly, I'm more trying to like tell you the theory behind it. Okay, so what is this? Well, this is just the same thing we had before, except now it's n minus 1. So we know, therefore, that, okay, we can write this as that for any n. For any n. Well, yeah, exactly, for every n. So therefore, if we invent some kind of rational modulus, then we can look at, so we have a rational modulus here that I just invented. Okay, so we know that this thing here, okay, this is 1 x plus 1 over x, which we assumed is rational and just from the beginning, and then this thing, and since this is our induction assumption, we assume that this is true. So this this also disappears. And since rational numbers don't depend on minus signs, we know that this now is, if in our modulus rational, because we know that, okay, a rational plus a rational is also always a rational, but a rational plus an irrational is, well, yeah, what this modulus does is just removes anything irrational, because adding a rational to an expression doesn't change if it's rational or not. So this is just x to the power of n minus 1 plus 1 over x to the power of n minus 1. So, and then we can just loop this thing around, basically, because we could just call n plus 1, sorry, n minus 1, n plus 1. It's just a dummy variable. So we know that this thing can then be expressed as this thing, but then you just subtract all the n's by 2, basically. So here we would have x, and yeah, well, yeah, you get the point. So here we know that this thing, also in our modulus rational thing, what would this be? Well, this thing would just be, we would just subtract by 2 again. Because if we were to start out with n minus 1 instead, we would have n minus 3 and then n minus 3 over here. So, okay, if you give me, okay, so no, first I'll explain first. Okay, so essentially what we can do now is that we know that this thing, modulus rational, is this thing, which modulus rational is x with just a minus 3 instead, and then that thing is rational modulus with x minus 5, and then we can just keep on doing this thing until we either reach, until, well, things start to, we have to, well, yeah, we can just repeat this until we either have like a 1 or a 0 or something like that, because we know that will eventually happen, because we can just repeat the pattern. So, okay, in case 1, we get that, okay, if n was even from the start, okay, so an even number, and then we just take, okay, sorry, if n is even, that means that this is odd, and then we subtract by 2, and then we subtract by 2, and so forth. So we will eventually end up with, well, n is just, well, yeah, n is still even. So we would end up with n is 2 at some point. And then what do we get then? We get that, okay, if n is 2, then we have minus 1, that's 1, x to the power of 1 plus 1 over x. And that we know is rational. And if n was even from the start, then we know that then we just keep on subtracting 2 until we reach, say, a 1. And then we would just get, if n is 1, then we get an x to the power of 0, which is just 1, and then 1 over x to the power of 0, which is 1. So and that would just be 2. And that 2 is, okay, sorry, yeah, I erased it. But yeah. And that 2 is what we got earlier from the normal factorization. Sorry, the normal parentheses expansion. So, okay, maybe you could tell me in the comments if you want me to like write this out more formally. But this is essentially, because this will take a lot of text to explain. Absolutely, it will. But I'm just trying to get across like the point, the idea is that we can keep on doing this thing because adding and subtracting rational numbers doesn't change the rationality of an expression, and we can just keep on subtracting 2 from the exponent, and then we either get down to a 1 or a 0, or sorry, a 2 or a 1. 0 also works, then they just flip. So then we end up with either at some point we will end up with a 2 or a 1. And if we have a 2 for an n, then we just get this expression. And if we have n is equal to 1, then we just have that this is x to the power of 0, which is 1, and then divided by 1. So that's just 2. And both of these are obviously rational numbers. So, well, yeah. So sorry for the possibly very confusing video, but I hope you liked it anyway, and I really hope I got my point across. Otherwise, this was pointless. So, well, yeah, that was basically everything for me. And please tell me in the comments if this was confusing or not. So, well, yeah, like and subscribe. Bye bye.